Okay, we want to develop the technique of integration by parts. And to understand where it comes from, we start with the product rule for derivatives and we work backwards. So let's recall the product rule for derivatives. So if we want to take the derivative of the product of two functions, we'll say f times g. It's the first function times the derivative of the second plus the derivative of the first times the second. All right. We are going to eventually work backwards, but first we're going to solve for that piece. So we're going to just kind of rearrange. So f of x g prime of x is equal to this side, the derivative of that product, f times g of x, minus this piece, f prime of x g of x. So all we did was solve for this, moved that over, and wrote it in the opposite order. Now, if we integrate both sides, so we integrate term by term, the left becomes the integral of f of x g prime of x dx, and the right side is going to be the integral of the derivative of f of x times g of x dx minus the integral of f prime of x g of x dx. Okay, if you remember the fundamental theorem of calculus, if we anti-differentiate the derivative, they cancel each other, and we have the integral of f of x g prime of x dx is equal to f of x times g of x minus the integral of f prime of x g of x dx. I'm going to rewrite this, the g first, so it really will become g of x f prime of x dx. And the reason I did that is because, so this right here is the expression for integration by parts, where this is the integral we're trying to solve, and we do it by naming part of that integral as f and the remaining part g prime of x dx. But normally we use u and v. That's pretty common if you've seen it before. So if we let u be equal to f, then du is equal to f prime of x dx. And if v is g of x, then dv is equal to g prime of x dx. So let's see what we have here. This right there then is u. This piece right here, g prime of x dx, is dv. That's just u times v. And then here we have v, that's our g of x, and this piece right there is du. So that is the common expression. Let me rewrite it here. So the integral of u dv equals u times v minus the integral of v du. And maybe you're like, so what did we just do there? Well, in essence, this is our integral, and we don't see an easy antiderivative for that. So what we do, our search here is to take part of it and name it u, and then the rest of that integral as dv. And once you have done that, then it's like you're going the product rule in reverse, and then you end up with this new expression, u times v minus the integral of v du, with the hopes that this integral of v du is easier and something that you can now tackle more straightforward. Okay, so that's going to be the idea behind it. And so now what you need to do is figure out what are you going to call u and what are you going to call v. Let's look at a classic example first, and then we will kind of come up with a process for how we choose our u and our dv. All right, so I'm just going to go ahead and tell you that let's call x u here, which means everything else is going to be dv. All right, so what did I just say? U is going to be my x, which means everything else is cosine of x dx is my dv. All All right, once I've named that, well, then the rest falls out, right? If u is equal to x, then du is just dx, right? Their rate of change is the same. Now we're going to go backwards here. So if dv is cosine x dx, then v, so the antiderivative here, is going to be a sine of x, right? Gotta be careful with the signs going backwards. Okay, so now that we have identified our pieces or our main players, we now can use our expression that we developed by working the product rule in reverse. So u dv, which is our integral, is equal to u times v, so x times sine of x, minus the integral of v, sine of x, du, which is dx. So everything now should be back in terms of x. All right? And now, this right here is an easy integral for us to solve, right? So then this is x sine of x minus, the antiderivative of sine is a minus cosine, so plus cosine of x plus c. So our original integral, x cosine of x, excuse me, dx is equal to x sine of x plus cosine of x plus c. So integration by parts is not bad. The trick will be what do I identify, what do I call u and what do I call my dv? All right, and basically, like, we're trying to figure out something that, what we call u, its derivative is better and not worse, or at least not worse. And then what we call dv is when our antiderivative is better or not worse. And that's still a little vague, but that's kind of your guidelines. So even more directive, I guess, is that this is kind of the useful guide. So you're going to assign, if you have these things in your integrals, you're going to assign the thing that appears first as your u and the thing that appears second as your dv. And I know that's not really clear yet, so let me explain. So if you have logs, and inverse trig functions, oops. This is algebraic, but I'm going to put polynomials here. Trig functions, different than inverse trig functions, and then exponentials. Okay, so what do I mean by this? Well, if you have something that has a log in it as well as a polynomial, then this chart here says that the thing that appears on my list over here, so log is on there and it's above polynomials, so this should be my u and this should be my dv. Okay, if I have arc tangent of x e to the x dx, well, inverse trig appears above exponentials, so this is my u and this is my dv. Okay, so this is some guidelines that might help you when you decide to tackle integration by parts. All right, I'm going to pause this video and we'll pick back up with some more examples that we worked through together.